In this video, we consider a standard problem from classical physics. That is, an object slides without friction on a sphere until it eventually falls off. Now, most of the time when people consider this problem, they don't work out the entire thing. They stop when they determine a condition for the object to leave the sphere. In this video, however, we will determine the entire trajectory of the object. We won't show every detail of the derivation, but it doesn't require much work to fill in the missing details. Consider a sphere of radius capital R centered at the origin. Since the motion takes place entirely in a plane, we only draw a cross-section of the sphere as shown here. At time t equals 0, the object sits at the top of the sphere at 0, r and has an initial horizontal velocity vector s, 0. We're going to take s to be positive, so the motion is always to the right and not to the left. Our goal is to find the trajectory of the object until it hits the ground at y equals minus r. Now, if s is large enough, then the object leaves the sphere immediately and never touches it again. Solving for that trajectory is very straightforward, something you might do in a first semester physics course. We want to point out, however, that the square distance from the origin, x squared plus y squared, always exceeds big R squared if s is bigger than the square root of gr. So we're going to call the square root of gr the escape speed. Now we want to note that if s is less than se, then the object will slide on the sphere for a while and then escape. But when it escapes, its speed will not be the escape speed. Okay, so it's the speed at escape time will not be what we're calling the escape speed here. So this is a little bit different from what you might see in celestial mechanics. So let's suppose that s is less than s sub e, so the object does slide on the sphere for a while. So the object begins moving at time t equals 0 and slides on the sphere until time t equals t sub e, the time of escape. Then the motion is ballistic, that is, the motion is entirely powered by gravity, until the object hits the ground at time t equal capital T. So if the position of the object is x, y, then it's convenient to define the angle theta as deviation from the vertical as shown. This is useful while the object slides on the sphere, not so much for the ballistic portion later. So while the object is constrained to slide on the sphere, there's a reactive force N that's normal to the sphere. So we write the vector n as its magnitude times a unit vector in the direction of n. So the vector xy over r is a unit vector in the direction of n. And so this way, the only thing we don't know about the reactive force is its magnitude. And when that reactive force goes to 0 is when the object leaves the sphere. If there's no friction or air resistance, then the only forces acting on the object are gravity and the reactive force. So Newton's second law gives us ma, or in this case we're writing the acceleration as x double dot y double dot, so dots indicate time derivatives, is equal to the force of gravity, 0, minus mg, near the surface of the Earth, plus the reactive force. The initial position is 0r, and the initial velocity is s0. Now, our goal is to rewrite the governing equations in terms of theta. So we split the vector equation into its component scalar equations, and we obtain m x double dot is the magnitude of the reactive force divided by r times x, and my double dot is minus mg plus the magnitude of the reactive force divided by r times y, with corresponding initial conditions. Now, to switch to theta, we let x be r sine theta and y be r cosine theta. And we differentiate those expressions twice and plug them into the scalar differential equations for x and y on the previous slide. If you multiply equation 1 by sine theta and equation 2 by cosine theta and add them together, then you obtain an expression for the magnitude of the reactive force. That is, the magnitude is mg cosine theta minus mr theta dot squared. So notice that depends on parameters mg and r and the variables theta and theta dot. Similarly, equation 1 times cosine theta minus equation 2 times sine theta gives us an ordinary differential equation for theta. So we have mr theta double dot minus mg sine theta equals 0. The corresponding initial conditions, the initial angle is 0, and the initial angular velocity is s over r. Now notice in the differential equation for theta, we could divide through by m, but the next thing we want to do is derive an energy expression, and we want to keep the units correct to make our physics friends happy. To derive energy conservation in terms of theta, simply multiply the ODE by r theta dot to see that the time derivative of the quantity in parentheses, 1/2 mr squared theta dot squared plus mg r cosine theta is 0. All right, so that means that the quantity in parentheses is conserved. It does not change in time, so it's a constant. So this gives us conservation of energy. And if we plug in t equals 0, we get a conservation of energy expression that 1/2 mr squared theta dot squared plus mgr cosine theta is equal to basically the energy at the initial time, 1/2 ms squared plus mgr. Now note that this equation for conservation of energy includes both theta and theta dot. And so we want to try to use this to figure out what theta is. Now we won't show every detail, but you can solve for theta dot as a function of theta and some of the parameters in the problem. This is a differential equation that is separable, which means we know how to solve it. You can also plug this expression for theta dot into our expression for the magnitude of the reactive force and get an expression that only depends on the angle theta and some of the physical parameters. So when that magnitude disappears, when it vanishes, that's the escape angle. And so the escape angle is the arc cosine of 2 plus s squared over the escape speed squared all over 3. This corresponding speed at escape is s sub e over the square root of 3 times the square root of 2 plus the initial speed squared over the escape speed. And this is less than or equal to the escape speed. So again, the speed at escape is less than or equal to the escape speed. So if we look at a plot here, if we look at the blue curve, then we see how the speed at escape depends on the initial speed s. And you can see it's slightly less than s sub e if s is less than s sub e. All right? So if s is equal to s sub e, then the speed at escape is the escape speed. That by itself is not informative, but it's a nice check on our work. The red curve shows how the escape angle changes with s. The horizontal tangent for at s equals 0 means that s has to be pretty large for the escape angle to change very much. For large s, the object leaves the sphere for small angle. Now, solving the differential equation for theta gives us a complicated function of theta. So this is unfortunate. First, we get t as a function of theta, where f here is an elliptic integral of the first kind. You can invert this expression to solve for theta, and you get to theta as another complicated expression involving the amplitude for the Jacobi elliptic integral. Again, this is complicated, but not too complicated because special functions like this are built into tools like Mathematica or MATLAB. In Python, they're available in SciPy, that package. The escape time t sub e corresponds to the escape angle, so we can compute that. Again, somewhat complicated, but not too bad. And after escape, the motion is ballistic. So we obtain the initial conditions for the ballistic part of the trajectory from the final position and velocity of the constrained motion. So you can see expressions for these two things here on the slide. They're somewhat complicated, but not too bad. And then for times t between the escape time and the impact time, we have quadratic dependence on time. Impact with the ground occurs at time t equal capital T, where y of cap t is minus r. This equation is quadratic and has two solutions, but we want the larger of the two because the other solution is less than t sub e, and that wouldn't be physical. So working all that out in detail, you can get a relatively nice expression for the impact time. Here we show an animation of the trajectory. You can see how the reactive force decreases in magnitude as the object slides, and the object leaves the sphere when the reactive force vanishes. Now here's an unpaused version of that trajectory. The range of the trajectory is the x value at the impact time. Again, a fairly complicated looking expression, but not too bad. And if you look at this carefully, you can find that the minimal range for s equals 0 is 1.46 r, and the maximal range when s equals s sub e is 2r. Of course, you can achieve ranges more than 2r, but only for speeds that are in excess of the escape speed. So the motion is never constrained to slide on the sphere. It'll be perfectly ballistic motion from the beginning. And finally here we show several trajectories for different values of s between 0 and the escape speed. All right, so you can see for small values of s, the green trajectories are all sort of compressed to the left, and then they spread out for the red ones. You can also see the minimal range there is about 1.46 r, and the maximal range is about 2r. And here we have now completed our discussion of